welcome to 6034 Fall 2020 edition. Today is recitation number 9 where we'll be talking about support vector machines. I'll just jump straight into the agenda and talk a little bit more about what support vector machines are. Whoops. Allow me to... Let's see. Okay, there we go. So support vector machines are, well, an overview of the agenda. I'm going to show you more conceptually how we draw boundaries in the style of a support vector machine, and obviously all the definitions and little components of support vector machines, the way we did with neural nets, ID trees, etc. And then we'll go into the specifics of calculating the individual values and the parameters, and then I'll relax the assumption that we're going to be using to simplify a lot of the math at the very end and show you ways in which people have handled it, and that would be the kernel trick. Okay, so before talking about support vector machines, I believe this is the third time in the series, touch upon the supervised machine learning. But this time, I want to bring with it a plot twist. In the previous two times, I've mentioned something about supervised machine learning. It's that the goal is, given data, I want to find some rule to classify new data. And I want that rule, obviously, to be the best that it can be. But now the goal is going to be to draw boundaries. And I'll show you what I mean. So this is going to be a recap of the previous two recitations. So remember to the k and n's, the k nearest neighbors recitation, when we were doing k equal to 1, when we were drawing boundaries by hand using k equals 1, we were doing this perpendicular bisector business between different pairs of points. And I'm just dotting them lightly. I'm not going to draw all pairs of points. And then we would have the perpendicular bisectors extend and then connect somehow. I'm not going to be extremely thorough. So I would have some sort of boundary like so. It's not meant to be precise. It's meant to be a recap so that you remember what we were doing on that recitation. So this is k and n's. And we were relying on the perpendicular bisector. And this was the style of this approach to this, how would I say it? If we're saying that supervised machine learning is drawing boundaries, then this is one style of supervised machine learning in this analogy that I'm drawing. The other way to do it was using individual features in the style of what that was meant to be in blue, in the style of ID trees. And so we would get these straight lines because we would use a single feature. And that's why I've also labeled the axes x1 and x2, because they're features of a vector x. So I've already given away, this is ID trees. And they are either x1 and x2, or I'm going to say x and y tests. And by that I mean we're testing individual features and drawing boundaries based on those. And then we have the neural network, in which you grabbed all the points and you put them in sequentially through the neural network. You calculated the error, then you changed the weights, and then you put either the same point or another point, and you change the weights again, and eventually you would get some line right through it. And I drew it relatively quickly because remember that in a neural network, we calculate the gradient based on the error. So if I get this line, this line that I drew right here, and it just barely classifies everything, but it does. It classifies all the points correctly. Then the neural network is going to, or the equation for the error, the mean squared error that we were using, is going to be 0, which means when we calculate the deltas of the weights, they're also going to be 0, so the neural network is just going to stop training. This is the best solution that it can find. But then we take a look at the boundary, and we think, well, in this area right here, the boundary is extremely close to this point, and here this boundary is extremely close to the other point. So if I get a green point that's maybe right here, it's probably going to be misclassified, and the same for a red point. If I get one here, it's probably going to be misclassified. And that is where support vector machines come in. So a bit of the basics, and then I'll deal with the circles at the very bottom of the page. So the support vector machines by design are binary classifiers. I'm going to be dealing with positive or negative 1. So those are going to be the labels I'll be using: +1, -1. Sorry about that. Then they are numerical classifiers. And what that means, I'm going to write not symbolic. Although I recognized I'm not going to define what symbolic is, because that's a whole separate issue. What I mean by numerical classifiers is, for example, if you remember the ID trees example in the ID trees and k-nearest neighbors recitation, I was building a greedy ID tree that was using orange foliage, yes or no, or bark is furrowed, or smooth, or I believe rough was the third feature. So those are non-numeric features. Here with support vector machines, we're only interested in numeric features, or in representing those features that are not numeric in with numbers, because otherwise the support vector machine is going to break. And now finally, for the punchline, the support vector machine draws a single decision boundary to maximize the margin width between the positive and the negative points. And intuitively, this is how it will look. So I have a positive point right here and a negative point right here. And I have this decision boundary. This could be a neural network, for example. It would probably be a neural network, because this line, or this boundary, classifies both points correctly. And it's not necessarily optimal, but it gets the job done. So this is boundary A. But that's the problem with neural network. It is a greedy search for a set of weights that will correctly classify the given points. So as soon as it finds a good solution, it'll stop. But support vector machines aren't a greedy search. They're an optimization process. So we are maximizing the boundary between the 2 points, like so. And there are other advantages that you'll see throughout this recitation of support vector machines over neural networks. So support vector machines will prefer B in this case to A due to the larger margins. Conceptually, that's what they do. Now let's look at how the layout is and label the different parts. So let's label these points A, B, C, and I'm going to skip a few letters and make this one F. You'll see why. Now I want to draw a decision boundary, just to start. And I see I'm missing a few numbers from the axis accidentally. This would be a 1, this is a 2. I'm going to draw the decision boundary now. I'm going to try my best to stick to blue when it comes to decision boundaries throughout the recitation. So needless to say, this is the decision boundary. I'm going to abbreviate it as DB or DB just because decision boundary becomes a lot to write after the 5th time. And I'm going to now add, let's see. I'm going to add the following. So imagine that we're zoomed in this case, that I have these 4 points, but I have a point here, a point here, a point here, and this whole area to the left is full of green points. And similarly, this whole area to the right is full of red points. So what's so special between these two, or these 4 points? And what's special about them is that they are the single closest points to the decision boundary out of the entire data. And I'll introduce the concept of support vectors here. So I'm going to have the legend be some highlighting. And I'm going to highlight 3 of them. I'll explain why 3 and not 4 in a few minutes. Let me finish adding a little bit of the backstory to support vector machines. So the intuition behind support vector machines is that not all the points are important when deciding a decision boundary. So that's again the difference between support vector machines and neural networks. When you train a neural network, if I misclassify a single point, that point becomes an error, and then I tune the weights to classify that point. But in support vector machines, I'm not interested in all the points. I'm interested in the points that are closest to the boundary, or closest to each other, right? Because classifying a point that is extremely far away from any other point of another class is easy. Classifying a point such as this one, which is fairly close to the start of the red points, is much harder, and that's where we focus our attention. That's why we're zooming in to these 4 points. And these 4 points, when we zoom into them, they are what determines the decision boundary. And so the points that determine the decision boundary, which also and not coincidentally are the points from the 2 classes that are closest to each other and closest to the decision boundary, those are called support vectors. And in reality, the points are the ends of vectors. So in reality, there's a vector that extends to each of these points and ends on that point. But we are referring to the points as the support vectors themselves because it's much simpler and easier to see. And that's one of the simplifying assumptions that we'll make here in this recitation in 6034. Okay, so we have the support vectors. I know I haven't explained why this one isn't highlighted, but I'll get to it in a couple minutes after labeling a little bit more. We have the support vectors, we have the decision boundary. Now I need to label the gutters. And the gutters are these lines, or these dotted lines. The gutters go through the positive and negative points closest to the decision boundary. Okay? And now that we know that, let's get to what I promised earlier. So we have 4 walking back. So we're zooming into these 4. So let's assume all other data is irrelevant. So just ignore these extra points I drew on the fly. We have 4 training points. We have 2 classes. It's a binary classifier after all. And we have 3 support vectors. And that is one simplifying assumption that we'll be making in 6034. I will explain it further in detail later in this recitation, but what you need to know now is that when we're dealing with a two-dimensional problem, we have a maximum of 3 support vectors at any one time. And I just so happen to have to choose A, C, and B instead of C, B, and F. And there are certain combinations of these points that I can't choose, and I'll show you what is the case later in this recitation. Now I need to talk about the margins. And I would be writing on the whiteboard all night if I didn't include some of this written down already, so I've pre-filled out some of the information. So I have the gutters now, and I have the decision boundary, and we're going to name this distance from the decision boundary to one of the gutters, because that's what we're trying to maximize. We're trying to put as much space as possible between the decision boundary and each of the support vectors. So that would be increasing the margin. And then we're calling the margin I misspoke. The margin is both, from basically twice the distance from the decision boundary to the gutter. Okay, I've already explained more or less what support vectors are, but just to refresh, that support vectors are the points that define the decision boundary. And so, by definition, if I were to, this is a point I didn't mention, if I were to remove B, the decision boundary would change, because B is supporting this decision boundary by being here. But if I were to remove it, you can see the line, the decision boundary could conceivably change to be like this. If I were to remove C, for example, I would also get a decision boundary like this. So moving the support vectors would cause the decision boundary to change, and you can quickly explain to yourself, at least preliminarily, if I were to remove F, the decision boundary wouldn't change. So that's already another reason why we're not considering it a support vector. And I've already written here that it's a special case. Okay, so now the different cases of support vector machines, and here I'll elaborate further on the case of F in the previous example. So when I have a 1D problem, a one-dimensional problem, I just have a number line, which means my decision boundary is going to be a single point. Allow me to catch up to my own notes. So first off, the decision boundary is a single point. And then there are only 2 support vectors. I'm going to start abbreviating support vectors as SVs. I'll be writing support vectors and decision boundaries along, so the abbreviations will become helpful. And now let's think about 2D. There are 2 main cases in 2D. This is the one we just saw. There's 2 points on one side, a point on the other side that's more or less in between the 2 points. and then there's 2 points that are right against each other. So first off, perhaps the more obvious piece of information, that the decision boundary is a line. Hence, both these lines, and in 6034 at the very least, in the simplifying assumptions, there are 2 to 3 support vectors max. And so, in order to address what we were seeing, we're defining support vectors as points that define the decision boundary. In other words, when removed, the decision boundary would change. In the example at the beginning, if I removed f, it wouldn't, the decision boundary wouldn't change. But if I go back, or let's see, yes, I'm here. I explained the example a little bit more. I'm just going to go instead of back forward. I could remove this point, and the decision boundary wouldn't change. But I could also remove this point, and the decision boundary would not change because of these two. I would have case 1 here. So in reality, I can remove either of these 2 points without affecting the decision boundary. It would just make the remaining point become a support vector. So the simplifying assumption in 634 is that there's a max of 3. So I'm going to say that this is a degenerate case. So if you see such a degenerate case, it's degenerate because which of the 3 are support vectors becomes ambiguous. But if you choose 3 points that support the decision boundary, then you may disregard the 4th point or the 5th point perhaps as a support vector. So you may say, okay, these 3 are the ones that I like the most, and therefore they are the support vectors, and all the rest aren't. That's a simplifying assumption. And the reason while we're on the subject of the simplifying assumption, what we're working with right now is a hard margin linear support vector machine. And by that I mean that in the examples that I'll be presenting and the examples with which we'll be working, there won't be points inside the gutters, because the support vector machine we're using has hard margins. So everything possible will be done such that no points are inside the gutters or inside the margins. And when I mentioned linear, is that all the data that I'll be working with is linearly separable. And with that, the linear separability, the definition of that means that all the data that I'll be presenting can be separated perfectly using a single line. So I don't need to draw multiple lines, such as in the XOR example for neural networks in the previous recitation. And then at the end of recitation, when I get to the kernel trick, I'll show you what happens when the data isn't linearly separable. There are ways to handle that as well. Okay, so I've talked enough about the 2D case, about the degenerate case, about how to handle it. Just pick 3, and then make sure that they make sense, and disregard the 4th one. In this case, I disregard this one. Now, in 3D and greater, the decision boundary stops being a line for obvious reasons, and now the decision boundary is a surface. But all the same principles apply. The gutter is a surface, and you're trying to maximize the margin. In greater than 3D, we're dealing with hyperplanes, but it's the same concept as well. Okay. So while we're on the subject of drawing boundaries, and I'm looking around my desk because I'm missing my presentation prop. No, I have it on hand. So the convex hull method is something that we teach here in 6034, of course, for you to visualize where the decision boundary is supposed to go. More specifically, it's a way of visualizing the decision boundary when it may be hard to see initially. Okay, and the next point is I'm going to do my demo here, and it's going to be a very not dumb, but a very simple demo. So imagine that you have a rubber band, and this is for problems where you're looking at something like this. So there are points all over the place, and you don't know how to draw a line there. So you take a rubber band. In my case, I couldn't find a rubber band, so I'm going to use a hairband, which for strange reasons I seem to have in my room. So I take this hairband and I throw it around the set of green points, and I let go. And I let the rubber band or the hairband contour itself around the perimeter of the points. So I throw my hairband on there, and it's going to take the following shape. And I grab another hairband, which I coincidentally also found in my room, and somehow it contours to that shape. And then suddenly, whoops, I may have not drawn the best example. Assume that this line classifies everything perfectly. Let's just assume that. It's just a random example. Then the convex hull method in this case allowed me to see where I could throw or where I could draw the decision boundary. And I'm going to go over the cases. First, I'm going to take my rubber band or hairband. I suppose I should trademark it at this point. The convex hair method. So that's one hairband. That's another one. And the number of mispronunciations seems to be going up as this recording draws longer. So I have that decision boundary. This case, as you might guess, I think it's a fairly intuitive labeling. It's a line and point case, because we have the two support vectors here and one here. Then our decision boundary is going to be parallel to the line. And we have 2 to 3 support vectors. In this case, we have 3. Let me just label them for the sake of practice, or highlight them, these. Okay, on to the next case. So again, let me practice my convex hair method. I throw my hairband around these points. So one thing to keep in mind is now that this is a lot easier to see, it may be tempting to try to extend these lines and have them meet and then draw the boundary there. But in reality, you want to really split the middle in between the 2 points that are closest to each other. So in this case, we're dealing more with Let me erase this. Before drawing the decision boundary, this is between 2 points in reality, not a line and a point as in case number 1. And in this case, the decision boundary is perpendicular to the line connecting the points. So this is very, very similar to KNNs and the perpendicular bisector method. KNNs. And then finally here we have 2 support vectors. Just to top it off, the decision boundary, and we're golden. Last case. So this is actually, and unfortunately, once more a degenerate case. Allow me to apply the convex hair method. I can promise you I did not practice nor come up with that name until I was recording. That was this hair of the moment, pun intended. There we go. So now that I ran out of jokes, let me actually cover some material. We have 2 lines this time. And the decision boundary is, oops, what did I do? I hope I didn't do anything. Is halfway between the 2 lines. And we could say it's parallel, but I won't say it's definitively parallel. This is a visual method, and I don't want to make any guarantees with a visual method. We won't give you nasty problems, at least within 6034, to trick you using the convex hull method. And then finally, 2 to 3 support vectors, mostly 3. And this is, again, a degenerate case. I'm going to randomly choose a set of 3 valid support vectors. I'm going to choose this one, and this one. So, whoops. This one. I could have done that. I could have also chosen this one, these 3. Any combination in which there are 2 on one side and there's 1 in between the other 2, so that they form a triangle. Okay. So that's it for the convex hull method, and that about covers all the intuition component of this recitation. Now we're actually going to get into a lot of the math, and even the math, thanks to the simplifying hard margin linear support vector machine that we're using, or that we're working in this recitation, a lot of the mathematics are simplified to a fair extent. But my goal in this recitation is to give you the essence, and even with what you will see, even with the simplifying assumptions, this is a very, very powerful concept, and what you'll learn here is directly applicable if you want to go even deeper into support vector machines. Okay, so let's talk about precisely what they do. So they classify according to a given equation that I'll give you in the next slide. Actually, let me not get ahead of myself. So there's a decision boundary, and there is a normal vector to that decision boundary, and I've written it here in yellow. It's the normal vector W. It's, as I said, normal vector perpendicular to the decision boundary. And this is a very important point to note. It points toward the positive points. Then there is the offset, or as many of you may recognize it, the y-intercept. And you may ask, why do I need a y-intercept in all of this on top of everything else that I seem to need? And you'll see why. So this is the data set that we'll be working with in this recitation. And we're going to go step by step, outlining each of the equations and each of the steps that I will use and how to get them in solving this problem. And by solving, I mean I have this data and I need to find a boundary through it. I need to find the gutters, I need to find the support vectors, and I also need to find the normal vector W, and I need to find the offset, so the equation that ties everything together. So first step is to draw the decision boundary. Easy enough. And then I need to write the equation for the boundary line. And it's going to be x equals 1.5. I left it over here for reference. Now, and you'll remember this from the neural networks example, I need to rewrite the equation in a form that I may use. And in this case, it's in the form w vector x vector plus b is equal to 0. Allow me to get a drink of water. Okay, so my throat feels much better now. Let's take the equation again. Oops. This time it's 1 times x plus 0 times y is equal to 1.5. I'm going to rewrite it just a little bit further. Okay, so I have that. And how do I get it to the form x w times x? And that is a dot product. And in 6034, we have a lot of students with very different backgrounds. It's very, very possible that you yourself don't have a very strong linear algebra background. And the following step may seem a little bit daunting. We keep the linear algebra necessary for this for this topic very minimal. So please don't be intimidated by the following step. And what I'm going to do is I'm going to repackage this equation. So you remember how we were defining a vector x in neural networks and in KNNs as a vector of features, right? x1, x2, x3, so on and so forth. So what I'm doing in this case is x is equal to the following two features, x and y. That's all I'm doing. So I'm going to write the vector x, which is x and y. I'm going to say this is plus negative 1.5. Nothing really changed. I just wanted to have a direct correspondence to the equation right above. This is equal to 0. And I'm missing something. So when I packaged the x and y into this vector form, I lost some information because I had the 1 coefficient and the 0 coefficient. And I want to quickly brush over what a dot product is. And when I take the dot product of these two vectors, what happens is x is going to be multiplied by the element over here, and y is going to be multiplied by the element over here. That's hard to see. X is going to be multiplied by this, y is going to be multiplied by that. And then in a dot product, once that multiplication happens, the two products are summed. So this is going to be a 1, this is going to be a 0. And if I apply the dot product, I get directly back to this. 1 times x, x times 1 is this, plus, according to the dot product, 0 times y. And then I would just basically open this little box and get minus 1.5 back. So I haven't changed anything. I've just changed the format and how I write it to be in vector notation. And that's 99% of the linear algebra that you will need in support vector machines in 6034. Okay, so I have something that resembles a W, an X, and something that resembles the offset. And it would seem that we're done. But let me make the following statement. I'm going to say that this is W vector prime. This is X, because it's just a set of coordinates, and this is B prime. And why do I say that? It's because, let's take a look at the decision boundary. If this is W vector, in reality, what's to stop me from making the normal vector infinitely large or infinitely small in magnitude? So this is where things start to get into play. If the W vector becomes large, the margins become very small. And I'll show you why in the following equation. There's actually an equation that defines the width of these boundaries to some extent. And so the equation that defines those boundaries is, if I say that the margin width m is m, 2 over the magnitude of the W vector. So that is the width of the margins. There's a mathematical proof that shows how to go from this Wx plus b to this margin width is equal to 2 over the magnitude of W. It's far outside of the scope of 6034, so I'm going to give you this equation and ask you to take it for granted that is the margin width in a support vector machine problem. Now the problem is, first off, when I first presented or first defined the normal vector, I said that the W points toward the positive points, right? If we look at this 1, 0, this points in the negative direction. So that's wrong. And if we quickly glance at the W vector prime and we take the magnitude of it, the magnitude is 1, which would mean that this m is equal to 2. And in reality, we have a margin width of 1. And I'll evaluate this more clearly in this next example. Okay, so from this equation in maybe 2 whiteboards ago, we got that the W vector prime is equal to 1, 0. And now we have equation 2, and I'm just going to apply that m is equal to 1 from there's 0.5 plus 0.5 equal to 2 over the magnitude of W vector, which means that the magnitude of the W vector is equal to 2. Yet the magnitude of W vector prime is equal to 1. So now we know, at least for now, let's highlight what we know so far. We know the magnitude of W is equal to 2, and we know that we know where it points. And if we think it's flipped, then we could just multiply. So we could, theoretically, we could rescale W vector prime from 1, 0 to 2, 0. That changes the magnitude problem. And we could multiply by -1, which changes the direction. But that doesn't solve one thing. We still don't know how we need to change the offset to match the change in the W vector. So we apply a third problem, and I've moved the whatever we found in the previous slide, the W vector is equal to 2, W vector magnitude, to this area on the right so that it stays visible. We don't lose that information. So first, I haven't said so explicitly, but so this is a good moment to define it. A support vector machine works the following way. For all points, the sign of the dot product, the operation that I quickly went over when I was rewriting the W and the X in the form of vectors, W dotted with X plus the offset is equal to that point's classification, yi. So quick clarification, yi is the class. So this is plus or minus 1. So whatever sign you get from this calculation is the classification of that point. That's how a support vector machine works, and that's also why we need to find the W and the offset that work with it after finding the decision boundary, of course. But there's another equation, and this is the general support vector machine equation, but we can make it even more specific for gutter points. And gutter points are not necessarily support vectors, although support vectors are gutter points. Not all gutter points are support vectors. In the case where we have a max of 3 support vectors here in 603 for that assumption. So for all points on the gutter, at least my points are on the gutter and not my head. So W vector dotted with X plus B is equal to plus or minus 1. And it's exactly plus or minus 1. And this is really, really powerful because all I need to do is pick a point from the gutter, multiply it with whatever I have as my W vector, and I can check if this point is a positive gutter point. I should get positive 1 by putting it through the support vector machine equation that I found so far. And similarly, if it's a negative gutter point, I should get -1, exactly -1, and that'll tell you how to rescale. This is not equation 2. This is equation 3. That's what's going to help me rescale. So this is 1, 0, 2, 2. So I've picked point C over here, minus 1.5 is equal to -1, which is point C's classification. And this is yet another example of a dot product. This time I'm not doing it in reverse. So 2 times 1 is equal to 2. 2 times 0 is equal to 0. And I have to sum the two products. So just a little bit more explicitly, For those of you who are new to the concept of dot products, this is what I get. 2 times 2 plus 2 times 0 minus 1.5 is equal to negative 1. So I get 0.5 is not equal to negative 1. So I need to rescale W and B. W vector prime and B prime. And that's precisely why I named them prime and not the actual W and the actual B. So I'm going to have my scaling factor C, and I'm going to rewrite the equation again. Okay, and now I know what the inside of that equation is, or results being, I know it's 0.5 from above. That's equal to negative 1, which means C is equal to negative 2. So now I have my scaling factor 2. Now with that, I can, this is not equation 2, this is equation 3. I'll correct the typo in the notes before posting them. They're posted in the description, by the way. Let's see. Where was I? Oh, yeah. So I've written the equation there. This is the C that I found in the previous step, and the equation with the W prime and the B prime. And I'm just going to multiply through the entire equation. So this is going to be negative 2, 0, and I'm not going to alter the points because these are coordinates. If I alter them, then I would be working with a different point. I can only alter W vector here. Plus 3.0. That is equal to negative 1. And I quickly test. This is going to be negative 4 plus 3. That's going to be a negative 1 equal to negative 1. That should be no surprise because I basically plugged an equation into itself. Then I'm going to write the equation for this support vector machine now. So this is my W dotted with X plus 3 is equal to, well, this is Xi. That is equal to Yi. Or the sign. The sign of this is going to be equal to Yi. Okay, and that means that W is equal to negative 2, 0, V is equal to 3. And I think it's also important to note that this negative 2, 0 is consistent with equation 2, or what we found with equation 2, where we saw that we needed to multiply by 2 and we needed to multiply by negative 1 again because we needed to point it toward the direction of the positive points instead of the negative ones. Okay, so we're not done there. We found W, we found B, but there's a separate problem to support vector machines, and I'll start elaborating. Let me grab another swig of water. And that is in the way that support vector machines are trained. Because when a computer does it, it's, in reality, what's happening is a sequential optimization. As I mentioned at the beginning, a support vector machine problem is an optimization problem. Of the margin. So by sequential, I mean we iteratively adjust alpha for each point to maximize the margin. And then I haven't said what alpha is. Alpha is how much a point supports the decision boundary. And of course, I'll go through an example and we'll define it even further. But this is one of the ways that support vector machines are calculated, and one of the reasons that they're actually very, very efficient in computers, because they can be solved in quadratic time. Because the first thing to note, and this is one very, very important property of support vector machines, that for all non-support vectors, alpha is equal to 0. Otherwise, alpha is greater than 0. And by otherwise, I mean that that the point is both a support vector and it lies on the gutter. Or that it lies on the gutter and it's a support vector. So why is this such an important point? And this is getting back to the greedy versus optimization approach and the intuition that the points that are closest to the boundary are the hardest ones to classify. So here what is happening is, if the alpha value, we consider the alpha value the weight of a point, or how it sustains the decision boundary, that's why I'm referring to it as the weight, then all points that are not support vectors, are not near the boundary, have a weight of 0, which means the number of points that we have to consider for such a problem, even if we have a huge pool of data, is actually extremely small. It's only those that are near the boundary. So this is incredibly, in terms of efficiency, this is a really big step. The other very nice step is that it can be defined in terms of the equations for the support vector machine can be defined in terms of Lagrangians, and it can be referred to as it is referred to sometimes as the Lagrangian dual problem. This is now starting to get out of the scope of 603.4, but analytically one can solve these equations and find the weight alphas. And the two equations that I'm going to be presenting are consequences of, or not consequences, they follow from all of that mathematical analysis. So we've distilled the mathematics down to the following two equations on top of the point in number 1, and we can use those to determine the alpha values of the support vectors that we have. So this is going to be, let me label this as equation 4. Equation 4, the sum of the support for all support vector I, for each of the support vectors I, the alpha value associated with that support vector multiplied by the classification of that support vector. Summing all those terms is going to be equal to 0. So if I have 3 support vectors, the alpha value of 1, how much it supports the boundary, times its classification plus the alpha value in the classification plus the alpha value in the classification for all 3, that sum is equal to 0. And I'm going to rewrite it in a way that is essentially, it's a different way of looking at it. So the sum of all the positive support vectors, or all the alpha values of the positive support vectors, is equal to the sum of all of the alpha values of the negative support vectors. And why is that? Well, let's take this equation briefly, and let's say I had 2 positive points and a negative point. So I had alpha, let's say A times plus 1 plus alpha B times, let's say, plus 1 again, and then alpha C times negative 1, and this is equal to 0 according to the equation. So I could have just moved this term over here, and then I get the above equation. The sum of the positive alphas is the same as the sum, or is equal to the sum of the negative alpha values. Let me erase this so I can continue with the third equation. This is going to be equation 5. Prematurely switched colors. Classic. Okay. The sum of the support vector, or through the support vector I, the alpha value of that support vector, times the classification of that support vector, so far the same as the above one, times the coordinate, or the vector of that support vector. So the coordinates itself in the examples that we're using is equal to W. And that's a very, very important result. What that implies, so the same as the above, the alpha value times the classification, but then now including the coordinates. And when you sum all of them, you get the W vector, the normal vector that we were looking for earlier. So W is equal to the sum of positive support vectors, and it's going to be the positive alpha times the x vector, positive, minus for the negative support vectors, the alpha negative, or the alpha of that negative support vector, and the coordinates of it. And this is this transform is in line with what I did above. I just multiplied by the positive or the negative one, and then I moved the terms around. And so with these two equations, or these four, they're in reality they're only two equations. They're just moved around a little bit. We now have a total of 5 equations to work with in support vector machines, and that can get very daunting. I'm going to do an example now in which I calculate the support vectors, or the alpha values of the support vectors in the previous example where we calculated W. And hopefully it becomes a little less daunting to have 5 equations. And I know it's not easier said than done. So I'm going to apply it to A, B, C, and then I've defined an extra point D, just so that I apply the first identity. So equation 2 says alpha A plus alpha B is equal to alpha C plus, I got ahead of myself. Alpha A plus alpha B minus alpha C, because I'm multiplying by -1. The classification of support vector C is -1, and then this classification is also -1, and this is equal to 0, which means alpha A plus alpha B is equal to alpha C plus alpha D. And now I go back and I see, well, non-support vectors have an alpha value of 0, and I see that D is way off in space over here, which means it's contributing absolutely nothing to my decision boundary, utterly useless. So this is going to be 0. The alpha value is going to be 0. And now I'm going to apply equation 5. And I'm going to write it in terms of vector notation, but then I'm going to break it down a little bit. So please don't be intimidated by the linear algebra. It's not going to be any harder than the dot products that we did earlier. So I have my W, 2, 0. And that is equal to, let's look at the equation one more time. That's going to be equal to the sum of the x's times their positive alpha values minus the x's and their negative alpha values, or the points that have the negative classifications. Okay, so let's do just that. Let me start with A, and A has coordinates 1, 3. Plus B, alpha B, which has coordinates 1, 1. Plus, I ran out of space. Whoops, not plus. Minus alpha C, because it has a negative classification. And coordinates 2, 2. Okay, so it looks a little bit daunting, but in reality, this can be broken down into 2 separate equations very, very easily. It's very straightforward. So I'm just going to take the top row of the equation and the bottom row and separate them. So 2 is equal to alpha A times 1 plus alpha B times 1 minus alpha C times 2. And now the bottom row, alpha A times 3 plus alpha B times 1 minus alpha C times 2. So I have 3 equations. I've written them right here. And we're in luck because we have 3 equations and 3 unknowns. So this is 3 equations, 3 unknowns. This is a system of equations that you can solve. And I encourage you, if your algebra is a little bit rusty, I encourage you to try solving the system of equations on your own. I'm going to give you the answers so that you can verify later when you try them out. I'm not going to solve them myself because I'm already past the hour and I still have other material to cover, so I don't want to take 2 hours in this recitation. But the solution is alpha A is going to be equal to alpha B, and it's going to be equal to 1. And then alpha C is going to be equal to 2. And I want to bring your attention to 2 different things. I was deciding briefly what color to use, but same one for both. The first one is the fact that alpha A and alpha B are equal. And that's the case because it's a special case, not because that's the norm. And the reason is because A and B are symmetrical around C. And then the other special case, or not special case, this one is actually the norm, but I want to bring your attention to it, is that alpha C is larger because it supports the boundary by itself. So what happens when alpha A and alpha B aren't symmetrical? Well, we start to get the behavior that I have drawn here, but let me discuss first some relationship between the W vector and the alphas. There's obviously, we already have an equation relating them, equation number 5, but there's more to it than just that equation. And that equation is actually a consequence of the relationship between the W vector, the normal vector, and the alpha values. And one way to see that is what happens to the alphas when the margins increase. So remember how I defined the margin width as M? So I'm just going to bring that back. Let's say M increases. Well, let's go back to our equations and think, okay, we had an equation, M is equal to 2 over the magnitude of the W vector. If M increases, so does this. But then that also implies that W must decrease because 2 is constant. W decreases, but then we also had the equation that W is equal to the sum of support vectors alpha x y. So if this decreases, this also must decrease. And the coordinates aren't going to change. The classification isn't going to change. So in reality, the alphas are the ones that are going to decrease whenever the margins increase. And if you think that seems a little bit unintuitive, think of it in terms of, or the way I wrap my head around it is in terms of gravity. Let's say I have some support boundary, decision boundary here, then if I have 2 points here, they're very close to the boundary, so they're really pushing at the boundary toward each other. But if they're farther away, then the gravity of the boundary is much less, thanks to the increased margin. So it's not mathematically founded, at least not the argument that I made. It's just some visual way that in which I keep this relationship fairly fresh in memory. And then the other question, which was actually the first one that I asked in the previous whiteboard, was what if points are not symmetrical, or the support vectors to be precise? Let me grab a little bit more water. So if the points are not symmetrical, then we don't get the case in the previous whiteboard where the alpha of A and the alpha of B are equal. Notice that B and C, C is equal to, not equal, C is closer to B than it is to A. And the way to test, more or less, which in this case you're looking at it and ask yourself, how do I know whether alpha A or alpha B is greater? So the way to do it, or one intuitive way of doing it, is I have these three. And now imagine that I deleted A. So I run into this case. And the original decision boundary is going to shift the following way. here, and here. Now let's go back. Let me delete B. And how is it going to change? Well, it seems that the shift when I delete B is much greater than when I delete A. And what that implies is that B was supporting the boundary much more than A. Right? So, removing B causes a bigger change. In the decision boundary than removing A. I'm not going to write it. And or that second half, and what that implies is that the alpha of B is greater than the alpha of A. So the supportiveness of B is greater because once you lose B, you get a greater shift in the decision boundary. And that's one intuitive way of thinking about this asymmetrical case and thinking which alpha value should have the greater value. Okay, and let me catch up on my notes. There we go. Now let's drop the assumption that the data is linearly separable. So we're now moving away from the linear support vector machine and we're moving into a more real world scenario. What happens if the data is mixed and there's no clear-cut line? So if the alternative to clear-cut line to separate the data, what if the data are not linearly separable? So we can apply transformations. And you may remember what was it? Recitation on k-nearest neighbors. It was k-nearest neighbors. We also discussed both different distance metrics, and we discussed one transformation, and that was polar going from Euclidean or Cartesian coordinates to polar coordinates. But that's not the only transformation that one can do, going from Cartesian to Cartesian to polar coordinates. And the other thing that we can do is we can replace the dot product with another. Oh, that's a weird cross between an N and an H. There we go. Another kernel. Kernel. Another function that transforms the space. So in reality, what happens if the data are not linearly separable? Then you either transform or you transform, is what you're seeing. So in the case of applying the transformation, the first bullet point, it's you take all your data and you move it all to polar coordinates. In the second point, you change the kernel function that you're using. And what I'm arguing here now is, by saying this, is that we're currently using something called the dot product kernel. K of U V is equal to U and V. And you might be thinking, where is this kernel dot product mumbo jumbo coming from? We were just multiplying W times X, and okay, that was a dot product, but it wasn't anything particularly special. How do you change that with something else without breaking a support vector machine? And I'll show you how it comes into play. So the current kernel I'm arguing is the dot product kernel. And what I'm going to do is I'm going to write the equation for a support vector machine. So the class of a point xi is going to be equal to the sign. I wrote it earlier of the dot product of w times xi plus b. That's going to be equal to, that's how the support vector machine classifies points. But now we have equation number 5. Which gives me an equation for w in terms of the alpha values. So I'm just going to plug that in. The sign of the sum over the support vectors j, alpha j, times the classification yj, times the point itself xj, dot product with xi plus b. All I did was plug in equation number 5. I haven't changed anything. And now what I'm going to do is I'm going to regroup things. I'm just going to use the associative property and regroup either the associative or the commutative property. The recording's getting long, so I'm going to blame it on that I can't remember which property, but I'm just going to regroup the x's and then leave everything outside. So far so good. This is alpha, the alpha value of the support vector j, the classification of the support vector j, and now this is my regrouping, the vector or the point xj dotted with the point of interest xi. So remember that this is the equation to find the classification of a point it might be unknown, or it might be that I'm testing, but I'm trying to find the classification of the point xi plus b. And now allow me to rewrite something. The sum is the same, alpha j, yj, but now I'm going to write the kernel explicitly. The kernel of xj and that's another j, sorry, xi plus b. So let's take a look at, or a closer look at what's happening here. And let me just rewrite this. Class of xi. I'm not going to write it out explicitly, I'm just going to say it verbally. So what is happening, well, as I point at the different terms. So if I'm trying to get the classification of a point xi, what I'm doing is, for all the support vectors, I'm taking the dot product of the new point, or the point of interest xi, with the support vector xj, and then multiplying by a bunch of other stuff. But this is the punchline of this. I'm comparing xi to all the other points, because notice this sum is going over all the support vectors. So this is I'm doing dot products with all the other points, which means, and I'm going to write it out because this is the punchline, we're using the kernel to determine, at least the dot product kernel that we're using, whether xi is more similar to the positive points or the negative points. So we're just comparing it. And that's what a kernel function is. It's a similarity measure. And notice I plugged in one equation and then I regrouped, but I didn't really do any fancy trickerying. I just plugged in equations, so I didn't change the inherent nature of a support vector machine, because I still have a function that classifies points according to the normal vector defined, and then the alpha values are the correspondent. Okay, so I want to go through common kernels. Oops, I lost track of my notes. But this is it's a good sign, because that means we're close to the end. There's the dot product kernel. I'm not going to rewrite it. The linear kernel is fairly similar. I'm going to stick with u and v, because if I write xi and xj, it's going to get very confusing. And that's going to be equal to u vector dotted with v vector plus b. And this is going to draw a line. So you could say that the dot product kernel is a special case of this linear kernel, just that b is equal to 0. Nothing particularly special, because it draws a line the same as the dot product of the dot product kernel that we were using onto the next one. The next one starts getting a little bit more interesting. The quadratic kernel. K of u and v is equal to u dotted with v plus b squared. And what this does is it draws any conic section. So you may recognize the squared exponent, meaning that this can draw parabola. That's parabola. But I did say it's a conic section. So if we're thinking about it in 3D, there's the center point, and it draws an outward spiraling, or not spiraling, but an outward increasing cone around it. So if we have that cone and we cut a horizontal slice, what we get is a U shape, so that parabola that I just drew. But let's say I didn't cut it sideways, I cut it from the top, and I'm looking at it from the top to bottom, or the other way around, maybe from the bottom up. Then what I get in 3 dimensions, or in 2 dimensions, once I go from 3 to 2, is this circle. So if I have the points, it's a cone that opens and encapsulates the circles from above or from below. So I'm going to say this is a 3D cone, even though both the parabola and the and the circle are different cuts of a cone. And then lastly, I can get a hyperbola from it. Okay, so I'm going to leave the quadratics right there. The hyperbola is also manifestation of the square and manifestation of the conic section. I'm not going to get into the details about the hyperbola, because 1, the time, and 2, it gets a little bit more complicated mathematically. More complicated than what I've already made it. So let's move on now from quadratic to a polynomial. So this is going to be k of u and v equal to, and you'll see this is a generalization of the previous two. So it's elevated to the power p. We don't have to say which power it is. So quadratic is just a polynomial kernel when p is equal to 2. Linear is just a polynomial kernel when p is equal to 1. Dot product is a polynomial kernel when p is equal to 1 and b is equal to 0. And what this does is it can draw more sophisticated curves such as this one. And notice that that's what we've been doing with the quadratic kernel, starting with the quadratic kernel, is when a line is no longer enough, we increase the degree of the exponent and we increase the degree of that p exponent, and that affords extra curvature in the decision boundary that we can draw. So one way that I intuitively look at these is that the curvedness is indicative of the degree of the polynomial. And then finally, the last one that we'll discuss today is the radial basis function. Often referred to as RBF. And this is going to be, it's actually the most intimidating out of all the equations we've seen today, in my opinion. E. And you know it's going to be bad when it starts with E. Negative 1 over sigma. The magnitude of u vector minus v vector squared. And that's all entirely is the exponent of E. What it does is, intuitively, when you look at what it does, and then I'll tell you a little bit more precisely mathematically what it does. When you look at it, is that it draws approximately circles around points. So depending on how you tune that sigma value that I wrote without really commenting on, then you can get the following behavior where you get a circle here, and you can get an individual localized circle around each point of a particular class. Or depending on how you classify or you tune the sigma again, you can get, and this is the more precise way of saying it, this is a manifold in multidimensional space, and you basically get the ridges. You're cutting across the manifold, and you get these ridges in the 2D plane, similar to how I was describing the conic section. And you get these are the manifestations, if you will, in the 2D space. And that's tunable with the sigma parameter. And needless to say, if you can just draw circles around each data point of a particular class, then this can classify any data set. And I think this is a good point to wrap up with the discussion of why we even bothered teaching a linear SVM instead of saying, okay, this is a support vector machine that has a radial basis function and it can classify everything. So why not just teach that? And This gets into a comment that I made in, I believe it was the Bayes recitation, and not the Bayes recitation, actually. It was the ID trees recitation when I mentioned Occam's razor. And Occam's razor, which I believe I misspelled in the video actually, is the belief that the simpler a hypothesis or the simpler a model, the better. This is a paraphrasing of the general spirit of Occam's razor, but with good intentions. Because let's suppose I have a data set, or the example that I worked with today in the recitation where we calculated the normal vector. Let's say I applied the radial basis function and I got a circle around each of the green points, and all the red points just stayed the way they were. And then I get a new green point. The chances that it falls inside the circle, especially a tight circle, around the other green points are very, very slim. So there's that problem, that the more powerful a model is, the more likely, especially in machine learning, the more likely it is to overfit the data. And then it'll perform poorly on new data that it hasn't seen before. And hence why we want to use, in this case, in this context, the simplest model possible that can achieve the best results. The other one is, the more powerful it is, in reality, or this is a personal belief, the less I learn from it. And because it seems the more powerful it is, the more it can do of anything. So if it solves a problem extremely easily, then you don't really get a chance to see the essence of the problem. If you apply a linear basis function to a problem with a lot of data without looking at it, perhaps you expend a lot of computational energy and you end up solving it, but perhaps a line would have been enough, and it might have even had better results. So that's why jumping to the most powerful function or the most powerful kernel or the most amount of layers in the case of a neural network right off the bat is not necessarily the best approach, and why, at least in my personal opinion, why choosing simpler models that work just as well is always to our advantage. And with that thought, I will leave you for today, and I'll see you on the next one.